Okay, so bivariate data and linear correlation part 2. We had looked at the formula for calculating the linear correlation coefficient R, which involves the numerator of the sum of squares of x, y, and the denominator is the square root of the product of the sum of squares of x and the sum of squares of y. And so if you have a look at these, they're very similar formulas, but they involve a little bit of work. The sum of the product of the xy, subtract the sum of x times the sum of y all over n. And this similar process has to happen to find the sum of squares of x and sum of squares of y. And so what I wanted to point out is that extensions tables are going to work best for figuring these things out. And in particular with Excel, because it will, did I spell that right? No. With Excel, because that's going to work best. So let's take a look at how we can use Excel for that. So if you set up some columns in Excel that have your X value and your Y value, and you can organize them in whatever way you like, then you will input all your X values. We are going to need a sum of the X values. So that can be found by just summing up that column. And do the same with the Y. We will get the sum of the Y values. Some of the other values that we need for these are to square each X value and sum those up. And square each Y value and sum those up. And lastly, take the product of X and Y. So in this case, it's 27 times 30 is 810. So we can ask Excel to do all of these things and then take some sums. And each of these values along the bottom are the ones that we're going to use for these formulas. So that's why I'm saying, rather than try to do all of this manually with a calculator, which it can be done, but the more variables you get, the more complicated it becomes. If you want to do it with Excel when you have that opportunity, then by all means do that. For example, in a test situation, you might only have 5 or 6 values, so it's doable for a test situation without Excel in front of you. But I would also suggest to draw a table and fill in values, just to keep it organized. Okay, so using these formulas then, we've got our values in green along the bottom of the table. So to find the sum of squares of x, the formula for the sum of squares of x, we need the sum of the x values, all squared, the sum of the x squared values. Then we need to have the sum of the x values, and that number is going to get squared all over n. And you can see, if we look back to the table, the sum of the x squared column. The sum of the x squared column right here, 13,717. And for the sum of the x values, 351. So we have 13,717, subtract 351 squared over, we have 10 bivariate data sets, and therefore we get a sum of squares of x to be 1,396.9. Doing a very similar process for sum of squares of y and sum of squares of xy. Let's look at this last one, for example. The sum of squares of xy. Well, we need the sum of the product of x and y column. So going back to our table, we have the product column right here, and we have a sum at the bottom, 14,257. And then we need the product of the sum of the x column and the sum of the y column. 351 times 380. All of that is over 10. And when you do the subtraction, you get 919. So in order to calculate R, these three values are needed for the R equation. Calculating R, we put the sum of squares of x, y over the square root of the product of sum of squares of x times sum of squares of y. And we find out that in this case, the linear correlation coefficient is 0.84, and generally these are taken to 2 decimal places. Now we look at this. Remember I said that values for R that are closer to -1 or 1 are stronger linear correlations, and values closer to 0 are weaker linear correlations. So this is a fairly strong positive linear correlation. Now, linear regression is when we draw a line to represent this. So although we know the correlation coefficient that measures the strength of the linear relationship, it doesn't tell us about the mathematical relationship between the two variables. So a linear regression, or a line of best fit, gives us a way to predict other values. So if we have, for example, knowing that a person can do 28 push-ups, with this linear relationship, we can then predict how many sit-ups they can do. And to do this, we calculate the line of best fit. So the line of best fit is a straight line model, best fitting line for the points that are plotted. To do this, we're going to need to find the values for B0 and B1, or B0, B1, I call it B0. The line of best fit formula looks like this: y hat equals B0, B0, and plus B1 times x, okay? This might look familiar to you. In first year, you studied y equals mx plus b. And there's the mx portion, and there's the b. They're just reversed. And it's just a standard way that it's done in line of best fit. Y equals mx plus b, we always put the x term first. So this tells us that b1 represents the slope of the line, and B0 represents the y-intercept. So that should bring back some memories from first year. Okay, to calculate B1, and we cannot do B0 first because the formula for B0 requires knowing B1. So that's why we're doing B1 first. B1 is the ratio of the sum of squares of xy over the sum of squares of x. And you'll see that we've already calculated those two values. So by placing those two in the ratio, we can find that number. For the y-intercept, or the B0 value, that is the sum of the y values, subtract B1, which is calculated in the last formula, multiplied by the sum of x, and the whole thing is over n. And again, these are from our tables as well. So those three values that you get from the tables, those are the ones we're going to need again. Actually, there are 5 values in the table. Computational formula, it looks like this, but I recommend we just stick with this one. Okay. So, finding the line of best fit for Mr. Mac's physical fitness class in comparison of push-ups to sit-ups. B1 is sum of squares of xy over the sum of squares of x. 919 over 1396.9. And B1 comes out to approximately 0.66. Using that value to calculate B0, because we need it right up here, I recommend that you do not round when you're going to use the calculation again. So notice I'm not using 0.66 there. We're going to get a closer value the less we round. This is straight from our table, extensions table. So is this one. And B0 is 14.9. So let's see. We put that into the equation for the line of best fit. Y hat is 14.9 plus 0.66x. And this allows us now to make predictions for other values of x that we don't have given as an ordered pair. So if a person can do 28 push-ups, then using the equation for the line of best fit helps us to make predictions about the number of sit-ups they can do. So for x equals 28, our y hat is equal to 14.9 plus the slope 0.66 times, we're going to sub in the 28. And we'll say, well, they can do about 33 sit-ups based on this model. Okay, we will see that there are extreme and unrealistic values of x and y that are outside of this domain that don't make sense. For example, negative values. But in general, we do have a range of values that are part of this domain that will make sense in this model.